Ammonites were marine mollusks with coiled shells that thrived for more than 300 million years before their extinction at the end of the Cretaceous. They belong to the class Cephalopoda, related to modern octopus, squid, and the chambered nautilus, sharing a muscular body and tentacles. Fossil records show thousands of species with varied shell shapes and sizes, from tiny spirals to shells over 2 meters across. Their name, Ammonite, comes from ancient references likening their coiled shells to the ram's horns of the Egyptian god Ammon. Over geological time, Ammonites became abundant index fossils, helping scientists date rock layers and reconstruct Earth's past environments. This film examines their shell structure, evolutionary history, habitats, and why Ammonites remain central to paleontology today. An Ammonite shell is a series of progressively larger chambers connected by a central tube called the siphuncle. The animal inhabited the outermost chamber, sealing older chambers with gas or fluid to control buoyancy and depth. Sutures are the intricate lines where internal walls meet the outer shell. Their complexity increased in many groups over time. Shell shapes varied: tightly coiled spirals, loosely coiled forms, and even straight shells, each reflecting different life habits. Thicker ribbing and stronger shells often provided protection from predators, while thinner shells improve mobility for some species. Modern imaging and 3D scans let researchers visualize internal chambers and reconstruct how Ammonites controlled buoyancy and movement. Ammonites first appeared in the Devonian and diversified rapidly through the Mesozoic, especially during the Jurassic and Cretaceous. Fossils are found worldwide in marine sediments from shallow shelves to deeper basins, reflecting broad ecological ranges. Because Ammonites evolved quickly and had wide distributions, paleontologists use them as index fossils to correlate rock layers. Mass extinctions and environmental shifts drove turnover in Ammonite lineages, producing pulses of innovation and extinction. At the end of the Cretaceous, Ammonites vanished along with many marine and terrestrial groups, marking a major boundary in Earth history. Their extinction remains linked to rapid global change, offering insights into how marine systems respond to environmental stress. Ammonites occupied diverse niches. Some floated in open water, others hugged the seafloor, and some likely swam actively as hunters. Their soft body included a head with tentacles and a siphon for jet propulsion and respiration, comparable in function to modern cephalopods. Shell ornamentation and color patterns likely had roles in camouflage, species recognition, or hydrodynamics, though pigment rarely preserves. Evidence from bite marks and preserved remains indicates predators such as marine reptiles and large fish hunted Ammonites. Juvenile Ammonites were likely planktonic, drifting in surface waters before settling into adult habitats, aiding wide dispersal. Their life strategies reflect a balance between mobility, protection, and reproduction that allowed broad success across marine ecosystems. Ammonites are invaluable to geologists and paleontologists for dating rocks and interpreting ancient oceans and climates. Their worldwide fossil distribution helps correlate distant rock sequences, making global geological studies possible with precision. New techniques like isotope analysis and CT scanning continue to reveal details about Ammonite diets, habitats, and internal anatomy. Beyond science, Ammonites inspire art, jewelry, and cultural references, linking deep time to human creativity and curiosity. Studying ammonites teaches us how life adapts to changing oceans and offers cautionary parallels for modern marine change. Ammonites remain emblematic of deep time, spiraled records of evolution that continue to inform science and spark wonder. If you enjoyed this video, don't forget to like, share, and follow Mind Beyond Time for more short stories about science, mystery, and the universe.